Hello, my name is Qihua Zhou. I'm going to share my work on fast Coflow scheduling via traffic compression and the stage pipeline in data center networks. This work is supported by the following 6 universities. Well, let's talk about what we have done. We will first follow this outline. The first 2 episodes are mainly about the network level issues in cluster frameworks performance and the motivation to promote our research. Then we will talk about the algorithm design and how to implement a system prototype named Swallow. After that, we will evaluate our approach via both trace-driven simulation and the real deployment. And finally, it's about the summary of our work. We will discuss the background first, including network bottleneck, existing network traffic schedulers, and the abstraction of Coflow. Okay, in many production environments, we observe that big data application in data centers often involve scheduling of data parallel jobs containing rich communication stage and are subject to limited bandwidth. Much previous work also evidenced that the phenomena about network bandwidth is the main bottleneck of data center applications. So here comes a question: how to facilitate cluster frameworks performance? A natural answer is that alleviate the shortage of bandwidth. So actually, some existing efforts have been paid on it, such as load balancing, communication reduction, and task separation. Unfortunately, they achieve only limited success due to their ignorance of job-specific communication patterns. So it's time to introduce the abstraction of Coflow. Well, based on flow, the abstraction of Coflow is proposed to improve network performance by using the application level patterns. A Coflow is defined as a set of flows within a same computing or communication stage. For example, the shuffle stage in MapReduce jobs. Thus, a Coflow completes only when all the related flows are finished. In other words, the completion time of a Coflow is determined by the slowest flow, and it has two main objectives: minimizing the completion times and meeting deadlines. Here we compare the patterns of flow and Coflow. A flow is a point-to-point transmission, while a Coflow is a collection of semantic related flows sharing a common application level goal. And we will show the superiority of Coflow scheduling. Two Coflows are described in this figure: the orange Coflow 1 and the blue Coflow 2. Calculating their time consumption, we can find that in 3 schedulers, the completion times of Coflow 1 are the same, but to Coflow 2, the Coflow level SEBF outperforms the other 2 flow level schedulers. For example, the per flow fairness and the FIFO. It turns out a fact about that the flow level schedulers such as SEBF cannot get a short Coflow computing time. We call it CCT for brief on average. Thus, the CCT reflects the entire time consumption of a stage. Here are some typical flow schedulers with their own objectives. However, we observe that they still bounded by the limited bandwidth. So We have a question: can we use some techniques to alleviate the bandwidth shortage? Um, of course, we can, such as the infinite band. However, these techniques requires significant changes of network topology or high hardware costs that may be unsuitable in some scenarios. So, what is our proposal? We plan to use an alternative approach that reducing the network traffic by using idle CPU resources to make data compression. The idea of traffic compression is not new. Many frameworks support it, such as Hadoop and Spark, but they conduct compression in a coarse-grained manner, unaware of flow characters or bandwidth states. Thus, to meet these two objectives, we propose the idea that traffic compression should be jointly considered by Coflow scheduling. So I'm going to talk about something about the motivation of Coflow compression, mainly about ideal CPU and compression space of intermediate data. Well, look at this table. We monitor the CPU utilization to physical servers running the high bench as our benchmark, and we observe that CPU may often be idle. In this figure with the black areas circled in red are the idle CPU periods. Specifically, the bandwidth is not abundant, such as megabyte. This phenomenon becomes more frequently. Um, so we hope to leverage these idle CPUs to operate compression. Okay, we summarize our observation in this table. Also, we recorded the intermediate data size on the compression and the uncompression in shuffle stages. Here, the shuffles can be regarded as coflows. From this table, we to different applications. There are many different applications in the table, and we can see the compression space of coflows. So it is feasible to compression the coflows in real deployment. So it is feasible to employ traffic compression into Coflow scheduling to meet the following objectives about CPU and bandwidth. And the most important goal is about accelerating the network level scheduling. Then we will talk about the algorithm design and as well as its challenge and principle. We mainly have three challenges. Here is the first one: how to formulate the Coflow scheduling with traffic compression. The answer is to propose the abstraction of volume disposal. Briefly, the volume is the remaining size of flows containing compressed part and the uncompressed part, raw part. The disposal is a process of scheduling a flow, including two ways. One is data compression stage, and the other is the network transmission stage. So our basic idea of compression is to slim the so-called flow volume more efficiently. Here we can obtain a relationship about compression stage and compression arguments. The left is preliminary relative arguments, and the right is our requirement to make compression accelerate our scheduling. The following equation should be satisfied. Here we have the equation. And here is the second challenge: how to make compression strategy. As we should capture flow characters and available bandwidth, we need to dynamic make our decisions. Thus, we have to consider the following desirable requirements. We use a pseudocode to describe our compression procedure. Note that a binary return value beta is defined. We enable compression when beta is 1 and disable it when beta is 0. Then it comes to the third challenge, how to determine scheduling policy. We follow the shortest remain time first, SRTF for brief, but with two extra objectives. One is scheduling a flow with compression is never slower than the case without it. Two is permission only occurs when new flows arrive or existing flows complete. So we propose to follow the fastest volume disposal first order, briefly called SVDF. We use an example to illustrate our FVDF compared with the typical SEBF inverse. We have two coflows. Coflow 1 is in orange and coflow 2 is in blue. Three flows are contained in coflow 1. Thus the width is 3 and the total size of these three flows is 10. Correspondingly, the width of Coflow 2 is 2 and the size is 5. We can observe that our FVDF is significantly faster than SVDF due to the compression. And the gray area is the time slices that compression is enabled. Thus, the average CCT in SEVF is 4.5 and in FVDF is just 3.25. It's time to talk about the implementation. As you know, we have implement FVDF in a prototype named Swallow, and we plan to open source on GitHub. Some typical system technologies are employed, such as time slice and priority classes. And we decide the compression parameters using time slice, and we guarantee starvation freedom using priority classes. Okay, we give an overview of Swallow architecture as a centralized cluster framework. It follows a master worker or so-called master-slave structure. The Swallow master executes cluster manager to monitor and allocate resources. The driver collects coflow information and make scheduling decision. The Swallow workers execute communication with master, and they send or exchange messages via push and fetch data via pull. Okay, we list some main methods in Swallow API, such as the hook interface for collecting flow information and the aggregation interface to make the merge operation of coflows. Swallow is implemented in Scala. We employ Arca for message pathing and something for object serialization. Swallow provides an option to control the coflow compression, including three compression algorithms: SNAPy, LZ4, and the LZF. Users can enable the compression by configuring it to true. The API is showing this table. Okay. Here are something about the codes to provide programming snippet, and we have embed insert Swallow into our customized Spark to invoke FVDF. You may write your configuration nodes like this. First, identify your app and define your master node. Then choose the compression format. Finally, set the so-called smart compress to be true to enable compression. The following code written in Scala shows a usage example for describing shuffle, a typical communication pattern in Spark. First, create your Swallow context handler and then collect Coflow infos and aggregate Coflows. After that, the MapReduce procedure can be sent and fetch data via push and pull. When scheduling is over, we can remove Coflows and release the resources. Okay. As we have developed a system, so we will evaluate some metrics in the system level. We will mainly based on the trace-driven simulation and real deployment. And we observe that Swallow can significantly reduce average CCT and network traffic. Due to the time limitation here, we will expose some typical but not all the experiment results. The first is the flow level performance. We compare our proposal with some typical flow schedulers on the different flow scales, and FVDF significantly outperforms them, especially when the flows are huge. And the second is about the Coflow level performance. We compare FVDF with some well-known Coflow schedulers such as SEBF on the different bandwidth. Due to the compression, FVDF can beat them, but we also observe that when the bandwidth is not quite abundant, the improvement may be not very good, or even with the same performance. And the third is the job level performance. We use HighBench as our benchmark, and we define a job is mainly comprised with two stages: the shuffle map stage and the result stage. Under these scales, from large to gigantic, our FVDF accelerates the job process. As we use compression, it may be also useful to discuss something about the selection of compression algorithms. We test Swallow on the different compression formats, and here we list 7 typical ones. We observe that the LC4 and the LZO have better performance, thus we suggest to use them as default. Moreover, we will show the performance of traffic reduction, and we can see that Swallow can well reduce network traffic on the different input data scales. And we also use here the two tables to summarize the performance evaluation. The first is about the acceleration of scheduling by up to 1.47 times in Coflow and 1.66 times in a job. And the second table is about the traffic reduction. Of course, Swallow is significantly reduced the traffic amount. And thanks to Coflow's compression, we can reduce the traffic during shuffles. At last, here is the summary. So, generally, our main work about 3 aspects: conquering challenge of bandwidth bottleneck, and the second is control compression in a fine-grained way, and the third we design a system prototype of Swallow, and we will open source our project on GitHub, and you can find it online. Okay, that's all. Thank you.